what we have to be careful of always is rounding errors. And all this statement here is saying when we use raw data, when you use a calculator, kind of like I told you before, to find the mean or anything like that, or the standard deviation, or a computer, you're going to get answers that may vary. I know you don't have a textbook, but from a textbook. That's because computers and calculators do not round the answers in the intermediate steps, and they can use more decimal places. So they use more exact values than any of your tables that you have that I've given you copies of. So don't stress about it. It says these discrepancies are part and parcel of statistics. It's pretty standard in statistics because you're not dealing with nice round integers. We're doing a lot of a lot of numbers that aren't just perfect, and that's okay. It's going to be rounding errors, and not to stress over that. So one more thing we want to talk about, and we said before, all that work we've been doing with finding confidence intervals and the mean minus the z sub alpha over 2 times the standard deviation over the square root of the sample, or plus, or whatever, any of that work is all well and good when the sample size is 30 or greater. Okay? But what's a minimum sample size needed? What's a minimum sample size needed for an interval estimate of the population mean? So what they've done is they've kind of derived from the maximum error of estimate, they've derived this formula. And it says, if necessary, round the answer up to obtain a whole number. What we're looking for right here is our sample size. That needs to be a whole number. So it says, if there's a fraction or decimal portion answer, use the next whole number for a sample size. Always round up. So let's take this formula here and use it in an example. It says a scientist wishes to estimate the depth of a river. He wants to be 99% confident that the estimate is accurate within 2 feet. And from a previous study, the standard deviation was 4.38 feet. So since we are looking for basically the sample size, he wishes to estimate the average depth of the river. How many does he have to test to find, so we can be 99% confident that the mean is going to lie within a certain interval? So we use our formula. Sample is going to equal z sub alpha over 2 times our standard deviation. I'm going back to the old way of writing standard deviation, over E there. That looks pretty rough. But E is our estimate. So plug in what we know. I know that z sub alpha over 2, well, I shouldn't, before I jump there, 99% accurate, if I can find it, one of these way back here, there it is, 99% accurate is going to be 2.58. 2.58. And then, so that's what's going to go in here for z sub alpha over 2. Our standard deviation, oh, you know what? I forgot one thing on our formula here. This is supposed to be squared. Right there. Okay. Our standard deviation is right here, 4.38. All over our estimate, which we want to be accurate within 2 feet. So we're going to do all that and square it. And I apologize how rough this looks, but we're just plugging things into our formula. And when we do that, we get 31.92. Now remember, that's our sample size. We don't want to leave it 31.92, always round up. So we're going to round that up to 32. So what does that 32 mean? It means to be 99% confident that our depth is accurate within 2 feet. We need to take at least 32 measurements. So this formula here kind of helps us say how many do we need to be as accurate as we can. And it's derived from that, maximum error of estimate. So this, along with confidence intervals, can kind of tell us how exact we have to be, or how confident we can be in our findings.